Good morning all. This is Khalandar Basha, working as Associate Professor in the Department of ECE, Institute of Aeronautical Engineering, Dundigal, Hyderabad. Today I am going to discuss the stepper motor interfacing with 8086. The slides are prepared by referring the textbook title Advanced Microprocessor and Peripherals. Authors are IARE and KM Butchandi. Publication is Tata McGraw-Hill, 2nd edition. Stepper motor is a device used to obtain an accurate position control rotating shafts. A stepper motor employs a rotation of its shaft in terms of steps rather than continuous rotation as in the case of AC or DC motor. So the stepper motor will rotate step by step rather than a continuous rotation. To rotate the shaft of a stepper motor, a sequence of pulses is needed to be applied to the windings of the stepper motor in the proper sequence. The number of pulses are required for complete rotation of the shaft motor are equal to the number of teeth internally present on rotor. The stator teeth and the rotor teeth lock with each other to fix a position of the shaft. With a pulse applied to the windings input, the rotor rotates by one teeth position or an angle x. The angle x may be calculated as x is equivalent to 360 degrees divided by a number of rotor teeth. So if I have n number of rotor teeth, for one rotation we need to give n pulses. For each one pulse, how much amount of rotation or angle rotate will be takes place is equivalent to the total rotation is 360 degrees. As we are having n number of teeth, so it is going to be rotated by an angle of 360 degrees divided by n. So after the rotation of the shaft through an angle x, the rotor locks itself with the next tooth in the sequence on the internal surface of the stator. The typical schematic of a stepper motor with 4 windings is shown in figure. So it is having 4 windings: winding A, winding B, winding C and winding D. If we want to rotate the stepper motor in clockwise rotation, so we have to give the pulse first winding A, then winding B, winding C, winding D for clockwise rotation. For anti-clockwise rotation, anti-clockwise means this is the direction. So the windings will be excited as winding A first, followed by winding D, followed by winding C, followed by winding B, again winding A. So for each and every time, depending upon the rotation, either it is clockwise or anti-clockwise, the sequences we have to apply to the corresponding windings. So for clockwise rotation, winding A, followed by winding B, followed by winding C, followed by winding D. For continuous rotation, we have to apply these pulses. So excitation will be takes place either one winding at a time. Otherwise, we can have a alternative sequence for exciting 2 windings at a time. So the 2 methods we can apply, either exciting 1 winding at a time, otherwise 2 windings at a time. So for anti-clockwise, as the rotor has to be rotated in the anti-clockwise, the direction of the windings will be excited in this manner: winding A, winding D, winding C and winding B. So a typical schematic of a typical stepper motor with the 4 windings is shown in figure 2. Winding A, winding B, winding C, winding D, we are arranged in a H-bridge manner. Now for excitation, a particular winding, the circuit which we are shown in figure 3 will give the schematic of it. How we can excite the winding A? Here you have a output port. So from 8255, this is 8255, which is programmable peripheral interface, is is going to send the pulses to the stepper motor. The basic data we are going to get from a processor. In this case, we are taking 8086. So now 8255 is driving the stepper motor. So these ports are output port. So one of the port which we are considering for 8255, for this is port A. Assume this port A, one bit, either port A0, port A1 till port A7, one of the bit is connected to this circuit. So now we will say how this winding A will be excited. That means it has to allow some amount of current to be flow through the winding. So for port A, this bit, either I can give the input as logic high or logic 0. So either we can pass logic high or logic 0. Now we will see the circuit, how it is going to be functioned for logic high. So first we will say if the input is at logic 1. As logic 1 means this is at a potential of VCC. At a potential of VCC. Now the transistor which you have placed, it is a NPN transistor. As the base of this transistor is connected to port A pin, which is excited with a voltage source VCC. So now between emitter to base junction, emitter to that is base to emitter junction, we are given a voltage greater than the cut-in voltage. Greater than the cut-in voltage. So now the transistor is going to be on state. As it is forward bias, the transistor is going to be on state. When the transistor is on, we can take this transistor is said to be short circuited. This transistor is short circuited. Now from VCC supply, the current will be flows through winding A. As this transistor is on, now it is going to take the low resistance path towards ground. Now we can say that some amount of current is drawn by this winding A from the VCC to ground. So this winding A is said to be excited. Winding A is excited. Now we will see the operation of the same circuit with respect to input that is at logic 0. So assume the input which we gave for the winding A through port A is at logic 0. That we can consider as ground pin. Now for this NPN transistor, the P terminal is at ground potential and the N terminal is also ground potential. The net potential between a base to emitter is equivalent to 0. As this is not a sufficient voltage to drive this transistor, so this transistor is going to be off state. When the transistor is off state, we can take this circuit is open circuited. So here the transistor is open circuited. As the transistor is open circuited, the current which is flowing from VCC and winding DA cannot be reached to the ground. So in this case, what is the current we are going to get is 0 as the transistor is in off state. So as no current is drawn by the winding, so the winding A is said to be inexcited or not excited. So this is how we can excite a particular winding by sending a proper signal to the port. So now with this, if I have a port A, some bit, I'll take some X bit. X is taking, X may be 0, 1, 2 till 7, any bit. So if port A, X bit is equivalent to 1, so what happens to the excitation? So winding A is excited. If the port A corresponding bit is equivalent to 0, this winding is said to be not excited because the transistor is not biased properly. If you given logic 1, the transistor is on state. So a current will be flows from VCC ground through winding A. So the winding A is said to be in on state. This diode, it is for clamping. If any excess amount of voltage is going to get, this will be short circuit. Now the excitation sequences of a stepper motor using a wave switching scheme for clockwise rotation is shown in figure. So we have said already the excitation for clockwise is starting from winding A, then winding B, then winding C, then winding D. So any winding, if it is 1, it is said to be excited on state. If it is 0, the winding is not excited, or we can tell this one as off state. So now as we want to take it is in clockwise direction, first exciting winding A, the remaining 3 windings are not excited. So we wrote VB is equivalent to WB is equivalent to 0, WC is equivalent to 0, WD is equivalent to 0. For the next clock pulse, in the second step, after winding A, we have to excite winding B. So winding B will be passed as 1. The remaining 3 windings will be given with 0. For clockwise, the next clock pulse is given for winding C. The remaining 3 are inhibit state. For the fourth state, we are going to excite winding D, and winding A, winding B and winding C will not be excited. As all the 4 windings are done, then we are going to do again the repetition, that is winding A. After that winding B, winding C, winding D. So these are the pulses we are going to be continuously send to the corresponding ports to excite winding A, winding B, winding C, winding D to have the rotation in clockwise direction for stepper motor. This is a single winding excitation. This is one type of excitation sequence we can have. The same windings, if you want to rotate in anti-clockwise, for rotating the stepper motor in anti-clockwise rotation, the order of the excitation we are going to give is winding A, winding D, winding C and winding B. So first clock pulse, assume winding A is excited, the remaining 3 are not excited, winding B, winding C, winding D are not excited. For the next step, winding D will be excited. So this is what the direction. Winding D is excited, winding A, winding B and winding C are not excited. For the next step, winding C will be excited, winding A, winding B and winding D are not excited. For the next step, winding B is excited, winding A, winding C and winding D are not excited. So as all the 4 cases are done, all the 4 windings are excited. Again, it is a continuous process. Then next step, it is a continuous like winding A followed by winding D, winding C and winding B. Like this, we are going to be give the sequence of pulses depending upon how many number of clock pulses are required for rotating to the specified number of rotations, either in the clockwise or anti-clockwise. So this excitation table 1 and table 2 are used for rotating the shaft in clockwise and anti-clockwise respectively. The next alternative scheme we are going to have for the stepper motor using the same waveform switching scheme, but here the excitation will be done 2 windings at a time. Again, for clockwise rotation, winding A, order is winding A, winding B, winding C, winding D. In this alternative excitation scheme, we are going to give the sequences 2 windings at a time. So in the first step, we are going to excite winding A, winding B, followed by next step winding B, winding C. In the next step, winding C, winding D. In the next step, winding D and winding A. So this will do 1 rotation or 1 sequence completed for the 4th windings. After that, again winding A, winding B. So in this alternative scheme, 2 windings are excited at a time. The alternative scheme for anti-clockwise, for exciting 2 windings. So the excitation will be takes place like winding A, winding D, direction we are taking, windings. So as 2 windings are exciting, first we will take winding A, winding B, then winding A, winding D, then winding D, winding C, then winding C and winding B. After this again, continuous process, winding B and winding A. The sequence which you are going to give for exciting either winding A or winding B or winding C, winding D, you can start with any winding. It is not mandatory to go for giving the excitation for winding A always. Next, we will see a problem statement regarding a stepper motor interface with 8086. The statement is Design a stepper motor controller and write an ALP to rotate the shaft of a 4-phase stepper motor in clockwise 5 rotation, in anti-clockwise 5 rotation. The 8255 port A address is 0740. So in the given value, the port A address they have mentioned is 0740H. The stepper motor has 200 teeth and the port A bit, port A0 is connected to winding A, port A1 driving to winding B, and so on. The stepper motor has an inertial delay of 10 milliseconds. Assume that the routine of this delay is already available. Right. Now, if the address of port A is equivalent to 0740, the A1, A0 bit will decide if it is 00, it is port A, 01 port B, 10 port C, 11 control word register. 11 control word register. So for port A address is 0740. For port B, the address is the last bit instead of 0 we have to write as 1. So that is 0741H. For port C, the address is 0742H. Whereas for the control word register, the address is 0743H. This is the address scheme we use for accessing our data transfer between the ports by assigning port A with the address 0740, port B 0741, port C 0742, and the control word register is 0743H. Now we will see how we can program the 8255 for designing a stepper motor control to rotate the motor in 5 clockwise rotation and 5 anti-clockwise rotation. Stated that the stepper motor is having 200 teeth. So for each rotation, how many pulses we have to give is equivalent to the number of teeth. That means in this case, 200 pulses we have to give for one rotation. As we required 5 rotations, the total number of pulses are required is 200 into 5, 1000 a decimal. That is 1000 in the decimal format. We require that number of sequences. In hexadecimal, it is equivalent to 64H. The schematic arrangement for the various windings, I am taking as winding D, we are connected to port A0, winding C connected to port A1, winding B connected to port A2, winding A connected to port A3. So in the problem statement, I'll change a little bit. So port A0 is drive for driving port D, port A1 it is for winding C, and winding B will be driven with port A2, and port A3 it is used for driving winding A. So here port A3 bit is connected for winding A, port A2 bit is connected for driving winding B, port A1 bit is connected for winding C, port A0 bit is connected to winding D of 8255. So with respect to 8255, these are output signals. These are output signals. That means the port A we have to drive, or the direction we have to assign is output port. For a design of a stepper motor control, we require only one port. For this case, we are selecting port A. The port AB and port C we are not using, and the mode of operation will take a basic IO or simple IO mode, that is 00. Now we will see the given values for the first case to rotate the stepper motor in clockwise 5 rotations. The port address for port A is 0740. The stepper motor is having 200 rotor teeth. As for 5 rotation, for one rotation we have to give 200 sequence pulses. For 5 rotations we have to give 200 into 5, that is 1000 sequences. In hexadecimal, we can take this one as 64H. For 1000 equivalent, 64. The port A 3 were used for driving winding A, port A2 for driving winding B, port A1 for driving winding C, port A0 for driving winding D. As per the schematic, I am taking these values. The stepper motor is having initial delay of 10 milliseconds. In the problem, it is stated the delay program is already available. No need to write a delay program explicitly. The port address for port A is 0740, port B 0741, port C 0742 and control word register is 0743. The excitation pulses for clockwise rotation, we have to give first winding A, followed by winding B, followed by winding C, followed by winding D. Again, it will be rotated winding D. So the sequence which we have to send here, if you see the bit pattern 100 in the hexadecimal, it is equivalent to 8H. 0100, it is equivalent to 4H. 0010, it is equivalent to 2H. 0001, the sequence we have to give is 1H. Again, it is a repetition by sending 8H. So if you observe the bit patterns for rotating clockwise, these bits, if I write initially the port A is equivalent to 8H, for rotating towards clockwise, we have to shift these bits towards right side. So go for shift right operation. Always it is depends upon which port we are connecting. So here winding D, it is connected to port A0, winding C, it is connected to port A1, winding B, it is connected to port A2, winding A, it is connected to port A3. So the port A bits we have to shift towards the right side for clockwise. Suppose if you have chosen winding D as port A3, winding D as port A3, winding C as port A2, then we have to rotate in opposite direction. So it is always depends upon how the schematic of the circuit you have designed. We have to send the pulses accordingly. Either it is right shift or left shift, it will depends upon how we are connecting. So as we are chosen the port A bit for winding D, port A1 bit for winding C, port A2 bit for winding B, port A3 bit for winding D. For rotating in clockwise, shift this contents towards the right side. For any 8255 for programming, first we have to configure the control word register. So for this stepper motor control, the port C we are not using. So this is a don't care. Either you can pass 0 or 1. That means port C we are not using for controlling the stepper motor. So either you can drive this port as output port or input port. So that's why I'm taking this one as don't care. Port B, don't care bit. As we are not using the group B ports, the mode for group B also I don't care. Port C upper also we are not using. So this is also a don't care. Whereas port A, we have to configure this one in the output port. So for output port, we have to write this port value is equivalent to 0. If it is input, configure that particular bit is equivalent to 1. If it is output, configure that particular bit is equivalent to 0. The mode of operation is a simple or basic IO mode. So the mode 0 we are going to choose for group A. And the ports are using for IO operation. So the MSB bit is equivalent to 1. The MSB bit is equivalent to 1. The next two bits are 0, 0. The port A bit is equivalent to 0. Port C group mode for group B, port C are don't cares. So the value which we have to write for the control word register is 1, 0, 0 and the LSB values are 0, 0, 0. So here I can write the configuration from 0, 0, 0 to next 0, 0, 0, 1. Like this I can have a different possible combinations as 1, 1, 1. From 0, 0, 0 to 1, 1, 1, 1 you can choose any value. Whereas the upper 4 bits as they are needed for the stepper motor control, for all the cases this is reserved. So now for the first case, if you see the bit pattern 1, 0, 0, 0 that is 8, 0, 0, 0, 0 that is 80H. For this case it is 81H. Like this, what is the last combination we can have is 1, 0, 0, 0. That means which is equivalent to 8FH. So the control word register value we can write for stepper motor control either 80H or 81H like this until 8FH. You can write any value. For this application, I want to select all the ports in output port. All these ports we have to write in the default mode I want to take, that is as output. So I'll write the don't care bits as zeros. So for this example, I'm taking the control word register value is equivalent to 80H. The possible values are 80, 81, 82 till 8FH. Total 16 combinations we are having. You can choose any one because port A is only used for stepper motor control. The remaining ports are don't cares. So any values we can pass. So I am taking the control word register value as 80H by considering all the ports default as output port. Now for writing the program, we will use the first statement, assume CS colon code for requesting a segment for code segment. Then we don't require any data segment. Straight away we will start with the code segment. For 8255, always it is desired to write the control word register initially. For writing the control word register, the control register value is equivalent to 80H. This we are going to be moving to control word register value. So that we will write the instruction move AL comma 80H. So for porting this one to a IO port, we have to use the out instruction. The value which is present in AL, only that one we can send to the port. So first we are moving 80H to AL register. Then this 80H will be sent to control word register through AL register. So that is out control word register comma AL. So here what is the control word register value? That is the address is equivalent to 0743H. The control word register address here it is 0743H. So in this place we can write that particular address. For generalized, I made this one as CWR. So after this, how many pulses we have to send? So we require total number of sequences are 1000 sequence pulses we have to send, which is equivalent to in the hexadecimal it is 64H. So we will move this count into a CX register. So move a CX comma 64H. This is for loading how many number of sequences we have to send for rotating the stepper motor in clockwise 5 rotations. The next one is the pattern which we have to send for exciting winding A is 88H. So why we are going to write the 88H is whenever you are rotating this contents, every time the excitation should be takes place from winding A, winding B, winding C, winding D. So here winding A, winding B, winding C, winding D as they are connected to port A0, port A1, port A2 and port A3. Initially we are exciting winding A. Next for next excitation for winding B, so we have to shift these contents towards right side by 1 bit. Next 0 0 1 0. Next 0 0 0 1. Suppose if I go for next shift, here I am going to get the value as 0 0 0. But this we have to get value as 1 0 0. Where it has to come is here we should have one more bit, that is port A4. That one we have to give as 1. This we have to get from port A5 in the previous step. So this is 1. Before that we have to write this one for port A6. Before that we have to write this one for port A7. Now if I write this pattern to the port A, so then I can drive all the windings continuously from winding A to winding D. By using, instead of passing 8421, 8421 like this 1000 times, we can go for iteration by writing 88H into the port A. Then we shift these contents towards right side by 1 bit for getting the next winding excitation. Next winding excitation. Again we go for one more shift. So the initial excitation we want to give for winding A. So for sending to port A, first we have to write the excitation to port through AL register. So first we will move the sequence to AL register. Move AL comma 88H. This sequence we have to send for port A. So we will write the instruction out port A comma AL. This label we will see later why we are placing this label here. The next one is after every rotation, we have to call a delay. So to call a delay subroutine, the call instruction we will use. So here one sequence we are given for exciting winding A. For getting the next excitation, so we have to rotate the contents of AL register towards right side. So for clockwise, we will write ROR AL comma 01H. As one sequence is done, we are going to decrement the count. So that is decrement CH. So the loop, it has to be iterate for 1000 clock pulses. So for that, we are going to check the count in CX register by the instruction JNZ. So if the count is non-zero, go to loop 1. So what is the loop 1 instruction? Sending the data to a port, right? So this is a continuous process. This will be repeated for 1000 clock pulses or 1000 iterations it will be done. Once all the iterations are done, the stepper motor is rotated in the clockwise rotation. So we can end the program by calling INT21H. Before that, move AH comma 4CH, INT21H, code end as end start to end the program. So this is a program for rotating the stepper motor in clockwise for 5 rotations. For anti-clockwise rotation, just we have to shift this sequence towards left side. The remaining steps are same. Now we will see the rotation of the stepper motor in anti-clockwise rotation for 5 rotations. So here also the number of sequences which we require for one rotation, we require 200 sequences. It is equivalent to the number of teeth. For 5 rotations, the number of sequences which we require is 200 into 5, which is equivalent to 1000 sequences. In the hexadecimal, it is equivalent to 64 H sequences. Right. Here, port A3, we are used for driving winding A. Port A2, it is used for winding B. Port A1 for winding C. Port A0 for winding D. So the excitation for anti-clockwise direction, first winding A, then winding D, winding C, winding B, winding D. Here if you see the excitation gets by shifting the contents towards left side by 1 bit. For first clockwise, the sequence which we are going to give is 8H, next 1H, 2H, 4H and 8H. Now we will see the program for stepper motor interface to rotate the stepper motor anti-clockwise for 5 rotation. Assume CS code segment. First we have to configure the control word register. The value which we are assigning is 80H. For that, move AL comma 80H. This 80H we are going to be sent to control word register through out instruction, out control word register comma AL. Next, how many clock pulses we are required? 1000 clock pulses. In hexadecimal, it is equivalent to 64. That we are moving into CX register. Move CX comma 64H. The first sequence for excitation, winding A, it is 88H. So move AL comma 88H. After this, we have to send this excitation for the port A. So for that, we will write the instruction is out port A comma AL. For getting the next sequence, we have to shift the contents towards the left side for anti-clockwise. Before that, we have to call a delay for every rotation. For providing 10 milliseconds, we will call a subroutine, that is delay. Next, we have to get the second sequence by shifting the contents towards the left side. ROL, AL comma 01H. As one sequence is done, we have to decrement the count, that is decrement CH. Next, JNZ L1. So this loop will be iterated for 1000 times. After that, it will come outside. Then we can end the program by using the instruction INT21H. For that, we have to move AH with 4CH. Then INT21H, end the code segment with code end S. To end the program, we use the directive end start. So these are the programs for rotating the stepper motor in clockwise and anti-clockwise. Suppose if you want to combine both clockwise as well as anti-clockwise for 5 rotations. Assume CS code segment, move AL comma 80H control word register value, move that one to control word register using out instruction, out control word register comma AL. The first sequence we have to give as 88H and the count is 64H. So we will move the count into CX register by using move CX comma 64H. Then the first sequence we will move to AL register, move AL comma 88H. This sequence we have to send for port A. So out port A comma AL. For getting the next sequence for clockwise, we have to shift these contents towards a right side after a delay. So ROR AL comma 01H for rotating one time. Decrement CX JNZ loop 1. So this program, it is used for 5 rotations in clockwise. Remember here, as we are considered port A3, port A2, port A1, port A0 for winding D, winding C, winding B, winding A. In this manner, we have to use ROR instruction. If the windings are connected in this manner, port A3, port A2, port A1 and port A0, if this is connected to winding A, winding B, winding C and winding D, we have to use ROL instruction. So don't go blindly. ROR is for clockwise, ROL is for anti-clockwise. It will depends upon how you are connecting. If you are connected in this scheme, go for ROR instruction. If you are connected in this manner, go for ROL instruction. Depending upon the circuitry, we have to shift the contents either left side or right side. Next for anti-clockwise, again load the count into CX register, move CX comma 64H. The first excitation will move to AL register, out AL comma 88H. This we have to direct to port A. So out port A comma AL. As one sequence is done, for getting the next sequence, we have to rotate this contents towards left side. So by calling a delay program for 10 milliseconds, then we are going to be rotate towards left side by 1 bit. Then as one sequence is done, decrement the count. So this loop has to be iterated. Still the count is equivalent to 0 in CX register. So for that we can check by using JNZ. If CX is non-zero, go to label 2. So that means 1000 times this will be iterated. Once it is done, the 1000 sequences, it has to come outside of the loop. Then we can terminate the program by writing move AH comma 4CH. Then INT21H, end the code segment by using the directive code endes. To end the program, we will write end start. So this is the program for rotating the stepper motor both in clockwise as well as anti-clockwise, 5 rotations each. As if you want to vary the rotations, the CX value we have to rotate. Then depending upon the windings, we have to go for either left shift or right shift. Thank you all. Today we have discussed the interfacing of a stepper motor with 8086 through 8255. We have seen the program for rotating in clockwise as well as anti-clockwise. Then the last program we have done for both the rotations, 5 clockwise rotations first, followed by 5 anti-clockwise rotations. Thank you all.
Like, share and subscribe. Hit the bell icon for more updates.